cuando empecemos, ¿no? ¿O estamos
Sí,
listos?
yo te aviso.
Ya.
De nuestra parte estamos listos.
Ya. ¿Es cuando empecemos, no?
Dale.
Hi, everyone. Welcome to our ALMA virtual tour. My name is Thais Mandiola. I'm a visitor coordinator here at the observatory. Today, we'll take a virtual trip to ALMA. This moment, we're actually joined by one of the astronomers of ALMA. His name is Jose Miguel Fernandez. You can see him. Hola, Jose Miguel, how are you? Welcome. He will be joining us throughout our tour of the, just tell you more about the general terms of what ALMA does and an introduction of a little bit of astronomy, the facilities, the different instruments that ALMA uses, okay? So during the presentation, actually, we'll have a Q&A box where you can leave your questions. And the idea is that during the tour, you have any doubts or questions, we'll be answering throughout, okay? So with the help of Jose Miguel too, yeah? So, well, before we begin, it's important to clarify that at this moment, there are no visitors to the site, okay, to the base camp where we usually have the public visitors. Due to the pandemic, we're not having any visits at this moment, okay? This is actually for health reasons and just care for the workers that are on site and all the operations that are happening. This also is because ALMA is not 100% yet on the operations, okay? So we're just getting on track again for being fully operative, okay? So, well, our virtual tour today will begin with a little bit of a brief of how the astronomy began. So here we have some images of the ancient astronomy. And for this introduction, it's telling you about for thousands of years, actually, humans looked at the night sky without any instruments, okay? They imagined constellations to guide their journey and measure time, name the stars and identify the cycle of the sun and the moon. This until about 400 years ago, when Galileo Galilei used a telescope for the first time to look at the sky, changing the way in which we perceive the cosmos. Some stars were in reality galaxies, cumulus or nebuloses, and they were able to observe these dark areas of the sky where infinite stars were invisible to the simple sight. So began the race to create each time more sophisticated telescopes to reach our cosmic origins in greater detail. There were also another race, which was to find the best place in the world to build astronomic observatories. They had to be in very high areas, with great atmospheric stability and without light pollution, or radio signals interference in the case of ALMA. So they found the Chajnantor Plateau. Here I'm going to show you a little bit of how it's distributed. We can say that, well, the antennas and the base camp are located near of San Pedro Atacama at 2,900 meters above sea level, and the antennas are at 5,000 meters above sea level. We also have our headquarters in Santiago, and we can show you this video where you can see how extreme are really the locations at this high site and Chajnantor. So what I was saying, that they found this area that is called the Chajnantor Plateau, located in the heights of the Atacama Desert. These are one of the driest deserts in the world. Here is where they lay some soft waves that are falling into the plateau This is light and in millimetric and submillimeter wavelength coming from space, a natural, rare, and very prized resource. It is known that these waves are loaded with information about our cosmic origins. So therefore, people thirsty of this knowledge have gathered here to collect and channel and analyze all this information. This is how the Atacama large submillimeter array, the largest telescope that exists, was born. Its creation was achieved thanks to the international efforts between Europe through the European Southern Observatory, ESO, and North America with the National Radio Astronomy Observatory, NRAO, and East Asia through the National Observatory of Japan, in cooperation, of course, with Chile. Yet we're giving the territory, and in this agreement, 10% of the observations goes for astronomers that are from Chile, and actually 85% of the people that work on the observatory are Chilean. Okay, this is one of the agreements for collaborating in this huge radio telescope. So more than 20 countries are joining in this collaboration and working together to understand the cold universe where our cosmic origins meets. I'm gonna show you here other video of our facility so you can see how is the place where we stay during our shift. Let me tell you that we work on shifts that now for the pandemic has changed actually, but it used to be 8 days of work and then 6 days off, but now it's 11 days of work and 9 days off. Okay, and that's the hotel, the residence that we stay in during our shift. And all this area that you see is called the ALMA Operation Support Facility, the OSF, that is located at 2,900 meters. And here's where most of the ALMA staff work. But the antennas, as we saw in the earlier video, is located at 5,000 meters above sea level. So it will be behind those hills that we see after the residence. So it's about 40 minutes drive to get there in the car, okay, in a car. So the Chajnantor Plateau is called that way because it has the name of the volcano that's located in that area, called Chajnantor. The name of this comes from Alicanantay culture, the language that is Kunsa, and the meaning is taking off place. Okay, just so you know, and well, as we saw in the earlier map, the administrative headquarters are located in Santiago. Currently, we have about 260 people working in ALMA. It's important to say that 85% are working that are Chilean, and as I said, at least 60% of the people that work in ALMA go to the facilities that we're looking at here in the video. In the area, where the antennas are coming from, many countries were assembled here, and it is really impossible for these antennas to bring in a whole piece, okay, because they weigh 100 tons. So in this base camp, in this location is where they used to assemble them. They were traveling in 2 pieces, okay, and arrived here in the base camp, and they started to assemble them to carry it in huge trucks. They're called the transporters to the area of the Chajnantor Plateau. We're gonna see a little video after about the transporter so you can see this huge machine. But first, I wanna tell you about these antennas and what ALMA observes. And we're gonna do it through this video that we have of why astronomers use ALMA, okay?
What if you could only see one color? Not that everything in the world would be the same color, but you could only see things that were, for example, green, and everything else would be invisible. Not such a pleasant reality, is it? Well, it turns out that in a way, it's true. When you look around you, your eyes see what scientists call visible light. And that light, the one we're used to thinking about, is just a very, very small portion of all the different kinds of light that exist in the universe. And most of them are invisible to our eyes. But there are animals that are not blind to those kinds of light. That's why snakes can see even during moonless nights, and bees can see the flowers with the biggest amounts of pollen. They can see lights that we, humans, can't. Snakes can see infrared light, the same kind that allows you to see if you put night vision goggles on. And bees can see ultraviolet, the light that gets your skin burnt unless you protect yourself with sunscreen. All these lights are part of the electromagnetic spectrum, where there are also radio waves, microwaves, X-rays, and gamma rays, all the other lights that we can't see but are essential to our daily life. Microwaves are used to heat up your food, and X-rays that can go through skin are used by doctors to see your bones. The thing is, the story of the universe, of galaxies, stars, and planets, is told through all of these different kinds of light. And because our eyes are no good to see beyond the visible light, astronomers created new eyes that allow them to see far more, telescopes that can see the invisible light. ALMA is one of those telescopes. It can see radio waves. Some places in the universe look dark to our eyes, but shine bright in radio waves. The places where stars are born, for example, are full of dust, which blocks visible light, and therefore they are very dark. But radio telescopes like ALMA can see straight through that dust. They can see stars being born. They allow the study of things impossible to study otherwise, like galaxies that are very, very far away, or even the birth of other star systems like our own.
Okay, great. Next one, we have another video that here you can see more about the technology of ALMA.
We can't touch the stars, fly through distant galaxies, or even on planets outside our solar system. So the only way we can really study most of the universe and everything in it is through light, the light we can see and the light we can't. That's why telescopes are so important for astronomers. They are machines for collecting light, all kinds of it. They're just like very powerful artificial eyes to look at the sky. The bigger the telescope, the better it can see. Why? Because bigger eyes, like owls' eyes, have a bigger surface, so more light reaches them, allowing the distinction of fainter differences in color and a sharper vision. Smaller eyes, like spider eyes, have less chance of capturing light, so they have more problems in seeing details, and everything is a little blurry. With telescopes, it's exactly the same. If light was rain, and telescopes buckets to collect it, it's easy to think that the bigger the bucket, the more rain it would be able to gather. Building very big telescopes, though, is not only expensive, but also difficult, and sometimes even impossible. So what if, instead of trying to build a gigantic bucket, you joined a lot of smaller ones together? Well, great idea. That way you would be collecting the same amount of rain, getting the same information, but in a much easier way. Even better, what if instead of trying to collect all the rain, you just collected some of it, with buckets spread in key places, so that you have enough to guess the characteristics of the rain falling? Well, that would be much faster and cheaper. That was precisely what astronomers thought years ago. By using several different small telescopes as one, they could see extremely fine details of the universe, just like if they were using a single telescope several kilometers across. They called this technique interferometry. ALMA works exactly this way. It can make 66 antennas work together as one very, very big telescope, making it one of the sharpest eyes to ever scan the sky. With the sharpest eyes of all, ALMA can study very faint light in the universe and capture images astronomers can't even begin to imagine.
Perfect. So now let's dive into a little bit more in the instruments that we were talking about, the antennas. In this case, well, here we have a graphic of how the interferometry that we saw in the video works. These instruments will be the antennas. You see, it has the parabolic shape, then comes the light into the subreflector, and we have an instrument called the front end, where we have the receivers. We will look into that a little bit further in the presentation. And then that signal is carried out in the back end to digitize and comes into the correlator. That will be this, that says correlacionador. This big computer that processes this information of the 66 antennas. But going into more of the instruments such as the transporter, because as said earlier, the antennas weighed 100 tons, so they couldn't be moved easily. So we had to build custom made these huge trucks that weighed 130 tons. We have two of them, Otto and Lore, they're called. And they actually they have the measurements of 20 meters long. As you can see in this video, we have Lore, 10 meters wide and 6 meters high. And it moves in 28 wheels in total, 14 each side. The empty weight of each 130 tons transportation of that much weight requires really a great deal of power. And each of these trucks, they equip with 2 diesel engines, approximately of 700 horsepower, and 2 1,500 liters of tank for diesel. Despite really their size and strength, these yellow titans are capable of positioning the antennas on the path with millimeter precision and keeping them connected to the power source throughout their transportation. So as said, the car ride from the base camp to the high side, it takes about 40 minutes, okay? And we drive, it will be like a maximum of 50 kilometers per hour, but these machines, they go very slowly because of the weight and just getting all the protection of the antenna. So they drive 20 meters per hour, and it takes about, it is almost 7 hours, the drive of the antennas to get to the high side. So it's a long drive. We have 2 operators of the transporters that you can see here in the cabin that's hanging in the middle will be where they drive it. And also they have the chance of driving it remotely with a control remote. So they're really impressive. There you can see the control remote that they use for driving the transporter too. So at 5,000 meters, the Changnan-Tor Plateau, the antennas have 16 kilometers in the total area where they located. And that's when these transporters come, because you have it's about 197 paths that will be the triangles that are in the ground. Let me see if I can show you some images of that. Because these antennas, they change location throughout the year. And in this, we have some of the images of that. These triangles are the paths where the antennas position and get the power, okay? So the transporters, they can change the location of these antennas depending on really the scientific requirements, okay? They can get in more of a compact array, very close by. And also in a long baseline array with the 16 kilometers of distance of each antenna. So all the process of this information that's gathered with the antennas comes to this big computer, that's the correlator. So this big computer is one of the biggest in the world. It is an equivalent of 3 million laptops, okay? And it's the most powerful supercomputer that's located actually at that altitude, of course, at 5,000 meters. Well, ALMA has 66 antennas, as we mentioned in the beginning, but each one of these does not work alone. To be able to conform these images from millimeter wavelengths captured by multiple antennas, we need absolutely colossal computer power that has a capacity, as mentioned just now, of very big number of computers, 3 million. So to be able to perform the same number of operations per second that ALMA does. So to exemplify this, your eyes really are connected to your brain through bunches of neurons. These optical nerves carry the signal from your 2 retinas to your brain, and your brain processes the signals and turns them into a beautiful 3-dimensional view of what is around you. Afterwards, it's important that the signals from your left eye, same as your right side, gathered at the same time, no? And the signals from the right side too. Otherwise, your vision will be very blurry if it's not at the same time that you get this information. More or less the same happens with ALMA. ALMA's eyes, the 66 antennas, are connected to this big brain that will be the computer, the giant computer, not by neurons, but by tons of kilometers of fiber optic cables that are throughout the Chagnan-Tor plateau. So these cables carry the signals from the ALMA receivers to the main computers. They're called this correlator. Let me see if we can show you a little bit of those facilities. This is located at 5,000 meters too. And you can see how that room is really is just with all the necessary factors to this processor's work. You need specific humidity levels and temperature. So that is all allowed in this room that you're watching in the video. We have one of the workers there checking one of the cards, and we have actually 2 correlators that maybe Jose Miguel can help me telling a little bit of this. So they have specifics for the different antennas. If you can join me on this information, Jose Miguel.
Hello, Thais. Hello, everybody. Yes, that's correct. We have 2 of these big computer systems called the correlators.
Mm-hmm.
And we normally use them with different sets of antennas. We have the main correlator called the baseline correlator, where we connect the biggest antennas we have, also the ones that sit very far away from each other. And we also have it's called the more compact array correlator, which we use with a different group of antennas that we also use in ALMA. These are smaller antennas. They have 7 meters in diameter, and they're very, very close to each other. And normally we use them in parallel, and sometimes both groups of antennas observe the same spot in the sky, but sometimes they observe different projects. So that gives us more flexibility. There are many ways to arrange antennas and correlators, but though that's a typical way we use them. One correlator for a group of antennas and another correlator for a different set of antennas.
Perfect. Yeah, so these images are actually more of the big correlator, no? The one that correlates, not the compact array. Well, another of the instruments that we have are the receivers. Here we can see the front end, the inside of this instrument, and that is located inside of each one of the ALMA antennas. To work properly, they must reach a very low temperature, these receivers. We're talking about 4 Kelvin degrees. This is nothing less than minus 269 Celsius degrees, okay? This system will become really the retina of ALMA to be able to absorb this light that we're trying to observe, no, of ALMA. These instruments are maintained in the front-end lab, okay, that is in the technical building that is located in the control, in the base camp, sorry, of ALMA. And we will have 10 of them, the receivers, in each one of the antennas. Now they're integrating the band number 1. And if you can tell us a little bit more about this information, maybe, Jose Miguel, of the different bands that we have in ALMA and the frequencies. If you can explain a little bit more of that, please.
Yes. Can you go back to the previous image, Thais?
Yeah, there it is.
Thank you. Yes. So each antenna at the very back of the antenna has this drum, and inside of this drum you have like different mini antennas, or we call receptors. The dish that you see is what we use to collect all the signal to get as much radiation as possible. Then it bounces back to the secondary mirror, or we call it a subreflector, and then it bounces back very concentrated through a hole that is in the middle of the dish. And right behind that hole is this barrel drum full of these receivers. And each of these receivers can listen or detect a specific range of wavelengths. And each specific range of wavelengths, we call them a band. So we work in different bands, and we assign a number or a name to each band. So we typically the lowest frequency bands, that's the band 3 and band 4, and then we can go to higher frequencies and we of course are not very creative, so we go band 2, 3, 4, 5, 6, and then all the way to band 10. But each band has its specific wavelength range, and we use them for specific reasons too. So different astrophysical processes emit in different wavelengths, so we need to use different bands to observe those. It's hard to make one receiver that will be able to detect all wavelengths, so it's necessary to build different ones for each different wavelength range. And each one of these, of the 66 antennas we have the same set of identical detectors. So we can choose which band each antenna uses. Normally we use the same band in all antennas if they are all working together.
Great, thank you, Jose. So here we have a video that is shown of the labs that work from the technical building. And in these images, we can see that they're testing the front end before it goes into the antenna at the high side. So they have a special truck that drives the front end to the high side, and then they can integrate it into the antenna. Yeah, so it will be just testing all the antenna movement, just in a very similar way to see if it reacts the proper way as it would at 5,000 meters. And here are some of the engineers working with the receivers too. So what they do definitely in the labs is just getting into the temperature that was mentioned at 4 Kelvin. And they have a cryo system and they test them, as you see, and they integrate each one of the bands that Jose was talking about. Okay, so that's the work that's done in the ALMA labs. Let me check here. Well, and about the astronomers, actually, they actually don't go to the high side to work. Yeah, they work also in the control room that will be in the technical building. We can see an image here. And that's where they move the antennas for the different observations, and together with antenna operators that we can see in this photo too. So they actually don't see the images that we would imagine that they will be seeing of the discoveries that is released on the press. So maybe, Jose Miguel, you can tell us a little bit more about that, because I see you often before the pandemic in the control room working. So maybe you can talk us through of the work that you do in ALMA and especially in the control room.
Thanks, Thais. Yes, if you can keep that image there, I can use it to try to tell a little bit of what we do. So as Thais said, astronomers normally don't go to the high side where the antennas are. Most of the people that work in ALMA, in Chaknantor and the OSF, they are not astronomers working with the observatory. What ALMA needs are engineers, technicians, people that work in software, people that keep the system running. It's a very, very complex technological system. So most of our colleagues are not astronomers. ALMA has a group of astronomers working, and we take turns to go to the observatory, and we stay in the base camp, the OSF, working in the control room. So there we make the final decision on what to do with the observatory, with the telescope. All our colleagues do an amazing job keeping the telescopes in good shape, do constant maintenance, everything works under spec, and we need to make the final decision on what to observe with the observatory, with the telescopes. So in order to do that, we don't decide ourselves what we want or what we think it's cool to do. ALMA every year asks all the astronomers in the world what they would like to do, what objects they would like to observe, what science it's needed to do with ALMA. And all the astronomers in the world every year send proposals. And ALMA hires a committee or asks a committee of experts around the world to recommend which are the most valuable projects that ALMA could do. ALMA cannot observe everything that is requested to do because we don't have enough time. So we select, or as a panel of experts, not ALMA itself, but an external panel of experts, select the best or recommend the best projects that we can observe. And each project has very, very strict observing conditions that need to be met in order to be run. In the past, astronomers with a scientific project would visit a telescope, sit next to the telescope, and control the telescope themselves and choose what to do. That way of working, it's not the most optimal for ALMA. So what we do, we study these projects that we get, we understand what are the conditions that these observations need, and we select the projects that best fit the current observing conditions in order to point the telescopes to them. So if a project needs really, really good weather conditions and a specific layout of the antennas, we need to wait for those conditions in order to observe it. And the layout of the antennas, we make a schedule, so we know how it's going to be during the year, but the weather conditions are very difficult to predict with more than a week, for example, sometimes with more than a day of time. So in real time, we evaluate what we can do and what we cannot do. So we tell the telescopes where to point, and we run an observation. Typically it takes an hour. And after that, we decide by inspecting the quality of the data if the observation can be used or not. And if it can be used, we send it to other colleagues who will work on all this huge amount of data and create what's something called a science data product, an image, spectra, or other ways of delivering the data that astronomers around the world need. So the picture that you see there, it's our colleagues sitting in the control room deciding what to do with the telescope. And once we decide what to do with the telescope, we need to check the quality of the data. As Thais said, normally we don't see a pretty picture of a galaxy, a planet, or anything like that. Sometimes when it's not clear if the quality is really good enough, we go into more detail and generate an image that will help us make an assessment. But normally we care about like the quality of the pointing of the antennas, if the temperature of the receiver is good or not, if all the calibrators that were observed were bright enough, that kind of things.
So all that you monitor in these screens that we see in the picture, no?
And all that information comes in the screens. Thankfully, we don't need to do everything by hand or by eye. There are many automated processes that assist us in this job, and they will alert us if there is something is not going well. And if that happens, we need to understand what is not going well. If a problem needs to be solved, we report it to our colleagues in the engineering or software department. Or maybe the problem was that the weather deteriorated very quickly during an observation and it needs to be repeated. So there are many things that need constant monitoring while we are operating with ALMA. And the main goal is to provide astronomers around the world the best possible quality data, so they can use it to do the best possible science with it.
And the main factors that you monitor, what are those? You mentioned weather. So what would be the good conditions for observing?
Our main, the main quantity that we monitor or measure is how much water vapor is in the air at the time we do the observation. These very faint signals that ALMA wants to observe, they travel through the whole universe, like millions of light years, or sometimes billions of light years before reaching us. But unfortunately, they have to go through our atmosphere before reaching the antennas and the detectors. And our atmosphere, among other things, has a lot of water. And the water vapor in our atmosphere prevent some of the signal of the radiation to reach the antennas. So the driest the air is, the best for us. So sometimes we have a lot of water vapor. Not very often. ALMA is a very good site to do observations, but sometimes we have bad luck and the weather is not good and we have too much water vapor and we cannot observe because the signal that we need is too faint or is completely lost. So that's one of the factors that we constantly monitor. And the other factor is how stable the atmosphere is. If the air above us is very turbulent, if it moves too much, the signal that reaches different antennas, it's hard to combine afterwards by the correlator, because we assume that every signal goes unaffected and reaches each antenna in the position where we know it is, and then we combine it. But if there's a turbulence, the path that the signal takes could be a little bit different from what we expect and makes it really hard to combine afterwards. So we can monitor how much vapor we have and how stable the air is. And combining those two quantities, we can decide what projects we can observe. If it's raining, we can't do anything, of course, or if it's snowing, then we just close everything and we put the antenna.
And if it's windy, because
or if it's very windy also.
Yeah.
Our main, always like the first priority is keep our colleagues safe, then keep the equipment safe. And then if our colleagues are safe and the equipment is safe and the weather conditions are good, we can do science. Because the conditions up in the high side can be very, very dangerous if the weather turns bad. So we are constantly monitoring the weather, not because to do science, it's to keep our colleagues safe.
And actually now the astronomers are more far away of the antennas now, no? Because you're having their control room in Santiago headquarters.
That is correct.
Not from the OSF. So if you can tell us a little bit of
we don't go anymore to the OSF, to near the antennas. I think we all miss it very much, but because of safety reasons for all of us, the people that are not really required to be there to do job in person there, the organization prefers to keep them away from the OSF and all the other colleagues. In my case, I work in the control room. When I used to go there, I didn't need to go to the antennas. I liked to go to the antennas, but it was not needed for me to go. So as long as I have a good internet connection and all the computers that I need, I can do it. I can do my job as well.
Yeah, perfect. So we have a question, Jose. Yes. Normally, what has been discovered with ALMA?
Well, when ALMA was planned many, many years ago, it had different goals, scientifically speaking. So when ALMA was built or planned, the people that thought about ALMA and made the existence of ALMA possible thought that ALMA was needed for different reasons. One of them was to study the creation of the first structures in the universe, the first stars, the first galaxies. So ALMA focuses on that, for example. ALMA tries to observe the faintest, furthest galaxies when they are forming. That's one of the goals, and many of the discoveries of ALMA had to do with that. Other aspects or other scientific interests were the formation of stars and planets, for example, within our own galaxy. That is something that ALMA is perfectly suited for, because the wavelength that we observe, it's a wavelength where the very cold dust and gas that where the stars and planets come from, it's how they emit. So with ALMA, we can see those cold clouds of gas before or when they're starting to create planets. With ALMA, we study also objects in our own solar system, or we also study galaxies that are not that far away from each other. So ALMA focuses on many aspects of astrophysics. And one of the topics that is also very interesting is that ALMA can also collaborate with other radio telescopes and create a very, very big telescope to see objects in really, really fine detail. So we observe stars, planets, galaxies, very far away galaxies. We study clusters of galaxies. All the range of astronomical objects that you can imagine, there's a possibility for ALMA to study and make great discoveries.
Black holes, yeah.
Black holes, the area surrounding black holes, that's true. Yes.
So we have another question. How often do you have to move the antennas?
Typically, we change the layout of the antennas maybe once a month or once every 45 days. So the more compact the array is, and by compact I mean how close the antennas are to each other. We can see if the antennas are very close to each other and the array is very compact, we can see a big piece of sky, but the resolution is not very good. So it's like, for example, seeing the moon with your naked eyes. But then we move the antennas a little bit far away from each other, and then we can see high resolution, finer details in the objects. But the piece of the sky that we see gets smaller. It's like putting binoculars. You can see the moon with a little bit of detail. Maybe you can see a crater or two, but the moon clearly looks bigger, and the piece of sky that you see, it's smaller. And then if we move the antennas very far away from each other, we can see objects with a lot of resolution, very, very fine detail, but we see a very, very tiny piece of sky. So instead of you can take off your binoculars and get a very good telescope and look at the moon, and you will see a crater with lots of detail, but the moon, you will not be able to see the complete moon. You will only see a little piece of the moon. So that's the kind of effect that we look for when we move the antennas with ALMA. We try to see things with a lot of detail, and we want to see things in their context, like with a big piece of sky. We can't do it all at the same time. We need to move antennas to get all the different image scales. Yeah. So we are constantly moving antennas in the end.
So how many different configurations ALMA has? That's an important point, so people know yes. That you can make different observations at the same time. How many of them with different arrays? No.
Let me see if I understand the question. So ALMA has a very compact configuration where all the antennas are maybe less than 200 meters away from each other. If you could like make a circle, they would fit in a stadium, for example. That's the most compact configuration. And the most extended configuration, you can barely see an antenna from each other. There are like more than 15 kilometers far away from each other. The further antennas, the longest distance. That's a big distance. And in miles, that would be maybe close to 30 miles or yes, or the other way around. But in kilometers, it's 15 kilometers, 16 kilometers. It's a very long distance, and it's really hard to observe that way for many reasons. One is the weather. When you have an array that is so big, the weather patterns are different from different parts of the array. So in some places of the array, you have high winds or higher humidity, more vapor, and in other parts of the array, everything is fine. So how do you decide when to observe? That's part of the difficulty. And also to correlate or to combine the signal from antennas that are so far away from each other is very difficult too, for technical reasons. And to do maintenance of those antennas that are so far away from each other is difficult too. Like you have like 3 antennas that need maintenance, or a problem needs to be fixed, and they are in opposite sides of the array. How do you choose where to go first? How do you spend your resources in order to keep them working? It's a very big technical challenge.
Yeah, but in the case of when you're observing at the control room, you have 4 different configurations, no? That is mentioned. That's the compact array. Then you have the very long baseline. Yeah, and you have these 4 antennas that are surrounding the compact array. They can do independent observations, no? We can talk a little bit of that, because this is important.
Oh, thank you. And now I understand better the question.
Yeah.
What I was talking before is how we work with the big array that we can move around. But we also have, as Thais mentioned, this very, very compact array. It's actually the antennas that we use in that very compact array are smaller in order to put them close to each other. So we can have a very big field of view with them. So sometimes when we are observing a target in very high resolution with the big array, we observe the same target in low resolution with a small array, and then we can create more complete picture or image of the object we are observing. And also we have antennas that we create arrays with them, but actually they work by themselves. So they create the very, very low resolution images that sometimes are needed to calibrate, for example, the flux of the objects that we observe. So we have different observing modes within ALMA, and many times we use them all at the same time. So we need to keep an eye on many different things that are going on when we are running observations.
And you mentioned before of the process for astronomers to get time for observing in ALMA, but what happens? How is the timeline when they get approved and then get the image? If you can talk us through a little bit of that, how will be the result?
So typically astronomers send their proposals within during the before April or March, and I need to check the calendar, but it's in a specific time of the year at the beginning of the year.
Yeah.
And those proposals are studied and they're analyzed by a panel of experts. And these days, actually, that is changing. Each proposal is not only analyzed by a panel of experts, but also by the other people that are sending proposals, because ALMA gets hundreds, sometimes thousands of proposals, and to ask a group of 20 people to read all of them and to make a good assessment of the quality of each proposal, it's a lot of work. And so in order to share the burden, no, not the burden, but in order to make it fair for everybody wanting to use ALMA, is that we are starting to use a system that says, okay, if you want to apply to use ALMA, you also need to invest time by analyzing the proposals of other people. And this can sound weird because like you're competing, you're reading and trying to evaluate the proposals of your competition. But in the end, it actually works. And it gives a very good idea what is a good proposal and what maybe it's not the best proposal. And those results are known several months after the proposals are sent. And then what we do in ALMA is that we get all these projects that have been approved, and we study what is the best way of observing them, what arrangements we need to do in order to get them observed with the highest possibility, because sometimes projects require so many the requirements of a project are so high that we never find the chance. They require like antennas that are very far away with excellent weather for a long period of time, and sometimes that just doesn't happen. So, but like typically a person sends a proposal and the data will not arrive until a year later, and that's how long typically we need to wait, around a year. No more than 2 years, but no less than a year.
And that information is for public, that you can get into the platform?
Eventually all the data that ALMA gathers becomes public. But the first year of the data, the data belongs only to the astronomer that requested it. So an astronomer sends a proposal, goes through this whole selection process, it gets accepted, and then when the time comes, the data is obtained. I mean, the telescope observes the object that the astronomer was interested in, and then the data goes to storage, and we send an email or a notification to the astronomer explaining them how to download the data or the results. And the astronomer has 1 year where anybody else can see the data. And so the astronomer can have like priority to publish something, to publish a scientific paper, to make a discovery, to say something new about the object that was observed. After a year, ALMA says, okay, you had enough time. We don't want people sitting on data forever. And we will let everybody in the scientific community to use the data that we got because you asked for it. So after 1 year, you lose priority over your data. 1 year should be enough to work hard on it and say something about it. But sometimes it happens that for some reasons, results don't come out, and then ALMA wants everybody to use the data. So the observations are well used.
Perfect. We have a question from YouTube, Diego Rojas. For the maintenance, how to work for planification analysis of data for decrease errors?
Can you repeat the question? Sorry, Thais.
For maintenance, how to work for just organizing the analysis of the data for decreasing errors.
So ALMA has a department, like the science department of ALMA has a specific group that their main task and goal is to analyze the data and create the science products that eventually astronomers will get. So they will gather all the data that the antennas got for a specific project. And what they do, they calibrate the data. ALMA is not that we observe a galaxy and then we forget. We observe the galaxy and we observe many other objects at the same time, which properties that have properties that we know. We know how bright they are in different colors, how fast they are moving, for example. And we use that information in order to calibrate this other object that, for example, we are studying. And a very important aspect of astronomical observing, and for ALMA in particular, is to calibrate the scientific data. When you calibrate things well, your errors can be very small. We know the uncertainty. So we always try to have the lowest uncertainty possible in any quantity that we measure. And depending how good our observations are done, that uncertainty is going to be very, very small. And when we provide the results to the astronomers that get the data, we tell them, okay, this observation has this flux, or this object is very bright, but you need to trust that brightness to 1%, for example, or 0.5% or 3%. And sometimes the reason for the errors are because the weather was not super good, or the object ended up being fainter than we thought it would be. But there is the whole process of data gathering and data delivery in between. There is this data reduction and data calibration that ALMA takes very seriously, and it's a very important part of the whole process.
Very interesting. And could you tell us what is coming for ALMA for the next years, if any projects?
Yes, well, it's always like it's plans, but for certain the thing that's coming soon, the new improvement is to have a new band. It's called the band 1. Right now, ALMA, it's very limited in observations when we have too much water vapor, for example. And we have to stop observing if we have more water vapor above a certain level.
Mhm.
So in order to observe with those weather conditions, we need a new type of receivers that work at lower frequencies that are not so affected by water vapor. So we have two benefits of doing this. We can observe when the weather is not very good, and we can also observe different astrophysical phenomena. That each band is good for different astrophysical phenomena. So that's the change or the improvement that will come soon. Most likely for next year, we expect to offer observations to the community in this new band. There are no plans for adding more antennas in the near future. Unfortunately, we would love to have more antennas, but there are no plans. Each antenna, as Thais said, it's a very expensive and big piece of equipment and requires a lot of work. So when the antennas were made, it was a big campaign. And to get an antenna to work properly, it requires a lot of time to calibrate and commission. So it's unlikely that ALMA will have new antennas in the short term. We are working in better ways of using the resources we have and improving the computational capacity of the correlators, for example.
Yeah.
The correlators will be faster. They will be able to handle more data, like different spectral ranges, combine the data of the different antennas in a better way. And that will improve also the quality of the data and the operations of ALMA. Mm-hmm. But maybe the most visible change, which would be to have more antennas, it's not going to happen in the near term.
Mm-hmm. Perfect. Yeah, I've heard about the correlator getting upgraded too.
Yes.
Yeah, because now it's over 10 years, no? So
yes.
it's kind of a,
yeah, we change our phones 1 year after they're made, and these computers are 10 years old.
Yeah, of course. So, well, I think we're gonna close now our virtual tour. I'm gonna thank you for joining us, Jose Miguel, and thank you for all the viewers that are watching us from Dubai, from here from Chile, and through our YouTube social network. Okay, so thank you very much. I hope that you enjoyed, and if you have any other questions, you can reach us through our social media. We will be very open to answer your questions. Okay, so goodbye.
Goodbye.
Thank you.